Ladies and gentlemen, welcome to Flexcompute's latest webinar. We're delighted to have our esteemed partner NVIDIA joining us for this session as well. Together, our mission is to empower engineering teams to design exceptional products and achieve groundbreaking results near real time. Today, we're diving into how GPU-powered solutions are revolutionizing engineering workflows by enabling faster, more efficient, and highly accurate simulations. My name is Yusuf Murad, and I'll be your host and moderator for today's session. We're thrilled to have Ian Pegler from NVIDIA with us today, a results-driven aerospace engineer with a wealth of experience in CFD. Ian's journey has taken him from the UK aerospace and oil and gas industries to pivotal roles at Siemens Digital Industries. Now at NVIDIA, Ian spearheads business development for computer-aided engineering, showcasing the transformative benefits of accelerated computing, from lightning-fast simulations to cost efficiency and sustainability. Ian is passionate about helping industries leverage cutting-edge technology to enhance product development. I'm equally excited to have Qiqi Wang, co-founder of Flexcompute and a distinguished professor at MIT, joining us today. Qiqi is a visionary in CFD and numerical simulation, passionate about pushing the boundaries of what's possible in engineering and physics. With a career rooted in groundbreaking research, Qiqi has contributed extensively to developing advanced algorithms and methodologies that enhance the accuracy and efficiency of CFD simulations. At MIT, his work has focused on leveraging high-performance computing and mathematical modeling to solve some of the most complex problems in aerodynamics, turbulence, and optimization. As co-founder of Flexcompute, Qiqi has brought his expertise to industry applications, leading innovations like Flow360, a GPU-native high-fidelity CFD platform. His efforts have empowered top automotive and aerospace companies around the world to accelerate design cycles, reduce computational costs, and unlock unprecedented simulation capabilities, transforming how industries approach product development. Ian and Qiqi will not only explore together with you how you can use GPU acceleration, and how it's not only speeding up simulations, but redefining what's possible in engineering design and innovation. From reducing turnaround times to tackling the challenges of complex aerothermodynamic problems, today's session is packed with insights you can apply directly to your workflows. And at the end of the webinar, we will have about 10 to 15 minutes for a Q&A session. During this time, Ian and Qiqi will answer all your questions related to GPU computing and CFD. So feel free to drop any queries in the chat as we proceed. And with that out of the way, let me now hand it over to Ian. Ian, the stage is yours.
Thanks for the introduction. Yeah, my name's Ian Pegler, and I'm going to talk a little bit to get us started about how GPU computing is really revolutionizing CAE. I like this slide because I think it kind of explains quite well where I think a lot of people are with simulation. So you can see the kind of journey from left to right here on this chart of where we've come from with simulation. You know, it really started as a research topic, and then, you know, we validated it, did a lot of validation to make sure we were getting the right results. And now in most companies I've seen, it's now, you know, being used as what I've described as a virtual test. So the kind of gray bar you see there, which obviously gives a lot of value to, you know, gives a lot of value. You know, reduce the amount of physical testing you're doing, and save time and money. But ultimately, for me, the real value of using simulation is to move further to the right and actually use simulation to fundamentally drive an actual better design, rather than just validating the design that's already been created. Actually have design closer to the design iterations. But there's obviously a lot of barriers to getting here, right? There's CAE has often been constrained by the, you know, on-premises HPC resources, needing a faster turnaround time to actually keep pace with design iterations. And also to do that, you just need to be running a lot more CAE as well, you know, and, you know, the CAE teams often are the same. So there are a few barriers to going and doing more CAE. NVIDIA can really help by trying to enable this idea of creating a kind of more of a real-time digital twin of the design. So like we said earlier, trying to get the simulation closer to the design iterations. So instead of this kind of very step-by-step iterative process of trying something, getting a result, going back. We want to try and get as close as we can to actually doing all of this in real time. So to do this, obviously, NVIDIA has built a whole platform to help companies like Flexcompute create these revolutionary, CAE tools. And a lot of that's built on our platform, and it could a lot of the tools you might be familiar with already, like for example CUDA-X. So these are the libraries, the underlying libraries that you can use to run various solvers directly on GPU. We have things like modulus to create AI models, and obviously Omniverse on the visualization side. So, and underneath all of this is obviously the hardware itself. But we've, spent a lot of time and then continue to work hard to build this platform to allow these kind of revolutionary tools to be created. And to do this, I feel there's kind of a journey that a lot of people are on, right? I mean, a lot of people today use on-prem legacy, CPU compute, which is, what many people have used for, the last 30, 40 years. But to get to where we want to be, where we're kind of leveraging these models a lot faster and doing these kind of design iterations and doing multidisciplinary design optimization, where we really need to run these models faster, we really need to move over to start with accelerated computing. So leveraging the GPUs to really significantly speed up these types of simulation, can be like 30, 100x improvements in turnaround time. And obviously, if you then eventually want to move to AI surrogates, then there's obviously a huge training data requirement for those models. And a lot of people don't have, maybe the perfect data source right now. So there's a need to be able to, run these models a lot faster if you're going to generate the data you need to build these surrogates for almost real-time feedback, if you want to do kind of a real-time digital twin. So, obviously some of you are probably familiar with NVIDIA, and immediately you kind of think of more of the kind of traditional graphics card side of NVIDIA, obviously from gaming, and then for kind of computer-aided engineering, the use of our cards to do kind of pre and post-processing visualization. So the traditional, viz workloads, which we still obviously do, for those pre and post operations, then we have a range of products that can help for that. But the way that I think that the place we've really revolutionized things in the last few years has been the solving, the kind of third box along there, moving from that traditional CPU compute over to the GPU compute. So I think that's really where the revolution has really, really happened. And that's what we'll talk a little bit more about today. So, I think nearly everybody's probably heard of GPUs, and they're used in training large language models, and obviously now for CAE applications. But I guess why is that? Why are GPUs becoming so popular? And ultimately, it's just GPUs are very good at doing a lot of things at the same time. It's by design a massively parallel architecture. From the start of the GPUs was born basically to be able to paint pixels all at the same time very quickly. So it's always been designed to do a large parallel compute. And what's changed in the last few years is obviously the CUDA to allow kind of general purpose computing to be run on a GPU. Also, just the support of just general purpose programming languages to run on the GPU has changed things massively. So this massive parallel compute is really been the game changer in making that more accessible to software developers. That's not to say CPUs aren't important. I think one thing that kind of gets confused, CPUs are still very good for certain tasks, but GPUs are great for those kind of parallel tasks, which obviously lends itself to things like, a lot of CAE tools, like CFD in particular. And, like I said, CPUs are still important. They still do some useful things for us. So, we do have an ARM-based CPU at NVIDIA called Grace that's available for those CPU workloads. And then we also have a combination of CPU and GPU with our Grace Hopper platform, and obviously coming up Grace Blackwell. So, if there's still things that need to run resident on the CPU, then they can. And we've got this ultra fast connection between the two to avoid any of the traditional bottlenecks of moving data between the CPU and GPU that people have had going between across the PCIe PCIe bus. And obviously, if a code, is fully running on the GPU, then running on our latest kind of Hopper GPUs is the way to go. And obviously that's often the way to get maximum performance, is to actually have everything running on the GPU to avoid that need to come out and wait for other things that are running on the CPU. So what does that mean as far as exactly what GPUs to use for kind of these type of applications? Because if you look up our GPUs, you'll probably see a whole ton of different GPU options, from workstation GPUs through to data center GPUs. But the real kind of, I think, game changer for us has been the H200 GPU, which Flexcompute use. And the reason why this GPU is, I think, really been a step forward for CFD is the fact that the amount of memory and memory bandwidth used by this GPU is significantly increased. So obviously, more memory, you can see 141 gigs of HBM3 memory, means that obviously we can run much larger CFD models on one GPU. And then that memory bandwidth, a lot of CFD codes, that's the limiting factor, is the memory bandwidth, basically being able to move things on and off the GPU. So that memory bandwidth, and then you can see on that little chart I've got in the bottom there that it's massively increased from some of our previous generations of data center GPUs. So you see the Ampere generation there, the H100, and the A100, then to the Hopper generation H100, and then H200, the increase in this memory bandwidth. So again, you can see that obviously it's over doubled between A100 and H200. So even GPU to GPU generation, we've seen some very large increases in performance for things like CFD. And obviously, we actually provide this in various form factors, HDX and PCIe form factors as well, depending on what servers that make sense for people. Also, you'll see on the top of those PCIe cards, and there's the NVLink connector as well. So we can put this ultra fast connection between the GPUs, which we call NVLink. Probably more useful, we found, for some of the AI applications. So, but it does provide this extremely fast connection between the GPUs. Okay, and obviously, one of the things that's coming at the moment, Hopper is the current generation of GPUs we're really targeting, particularly the H200 for these kind of CFD applications. But obviously Blackwell is coming as well, right? That's the next generation of our data center GPU you may have heard of. And this slide here gives you just an overview of the Blackwell platform. And there's a lot of different things that make it up. I think a lot of people just obviously immediately think of the GPUs themselves, but things like InfiniBand, the quantum switch you see there for very fast, reliable connections between the different GPU nodes. Obviously, the NVLink we've already spoken about. And then obviously in GB200, again, it's a great Blackwell combination, but we've got the combinations now of two of the CPU to 4 Blackwell GPUs, so what we call the MVL configuration, which I think is going to be super interesting for CAE applications. And then obviously built on top of that hardware layer, you can see there we've got things like, again, our CUDA libraries, which we spoke about earlier, things like Omniverse to allow developers to really build these kind of game-changing applications. So just a kind of summary here. So ultimately, the GPUs, the massively parallel architecture of the GPU has allowed these huge increases in performance that I think you'll hear about shortly. So it has been a real game changer, but as well as obviously just the pure turnaround increases, then we also, to get this equivalent performance of GPU on CPU, that you'd have to spend like a ridiculous amount of money to get that performance. And even you have to assume that the code would scale in a way to get that performance. So, for the same performance, it's actually, lower cost. And then the biggest thing, right, is in the middle there, reduced design cycle time, right? Ultimately, what we all want to do is actually make these products faster, better products faster. And that's really what we're going for with the whole platform. So yeah, hopefully that gives you a kind of a quick intro to kind of accelerated computing. Obviously, if there's any questions for me, just stick them in the chat and we'll get to them at the end. But with that, I'll hand it over to talk a bit more about Flexcompute and Flow 360.
Hey, good afternoon, everybody. My name is Qiqi. I'm a co-founder of Flexcompute and a professor in the Aeroastro department at MIT. Today, we're going to be talking about innovation with high-fidelity CFD using Flow 360. I'm going to start by telling a story, a very old story. So those who do fluid mechanics probably knows this little poem. Big whales have little whales which feed on their velocity. And the little whales have lesser whales and so on to viscosity. This is, I think, one of the best description of what turbulence is and is very popular among our community. And many people knows that this poem is written by Louis Fry Richardson, the same person behind the Richardson extrapolation, right? Or like people who are studying numerical methods or know about. But I found that very few people knows where this poem is originally from. I did a little bit digging and found that it is from a book. It's from a book called The Weather Prediction by Numerical Process. Okay, the title of the book is actually pretty amazing given that it is written in 1922. Again, 1922, that's almost 30 years before the first electrical computer actually came online, right? So talking about the numerical weather prediction, which is exactly how we are doing weather forecast today. We feed the initial condition of today's atmosphere, like all the temperature, velocity, density, etc., into a supercomputer and solve it using numerical process to forecast the weather. And he's talking about this almost 30 years before there is any computer, not saying supercomputers. So this is basically why I'm talking about this is that Louis Fry Richardson is a visionary and he has a dream of doing numerical weather prediction. And today we're going to be sharing with you the dream of also Flexcompute and tell the story of Louis Fry Richardson together with a story of Flexcompute. What dream do we have? Okay, so first of all, why do we have the dream? And the next slide, please. So hardware innovation has been a lot more difficult than software innovation. So I did my PhD at Stanford and then went on to teach in aerospace engineering at MIT. And during these 20 years of learning and teaching, what I found out is that almost all the smartest people, even in departments like aerospace engineering, ended up doing software rather than hardware. Well, there is a small minority of very smart people who actually exactly knows what they want to do and stuck to doing aerospace engineering. But majority of the people, actually the most smartest people, they went on to do something else. And almost always it's software. So I've been reflecting why that is the case. And the answer is actually quite obvious. If you go to do software, it's remarkably easier in the sense that you only need a very small team to make something big happen. And the time frame that you start from an idea to actually something that changes the world is very short. It can be months or at most a few years. And it's almost risk-free in the sense that the worst thing that can happen is your startup goes under, right? And nobody dies, and you spend a few years going through that. And this is why, like when I was young, there was all this prediction about by today, like 2020s, we are going to be taking vacations on the moons and flying like, I don't know, all the places in the solar system. But instead, what we get today is things people never predicted, like the internet, software innovation, like social media, another software innovation, and artificial intelligence today, like purely software innovation. So hardware innovation has been going much slower than software innovation. And this is because hardware innovation is risky. It costs a lot. And for those who actually had any taste of both software innovation and hardware innovation, it's very hard for people who didn't have both experiences to actually appreciate how much more time doing anything with hardware actually takes compared to doing things with software. So the reason Flexcompute has this dream of trying to make hardware innovation as easy and as fast as reduce the risk, right? Reduce the cost and accelerate hardware innovation. This is our dream. This is why we founded Flexcompute, is to make hardware innovation as easy as software innovation. So our vision is in the future, maybe 30 years, 20 years from now, doing hardware innovation is going to be as easy as software. People with a small team or even a very smart individual in several months of time, at most a few years, is able to make new hardware, maybe new airplanes, new spacecraft, something that changes the world. That's as innovative as Google or OpenAI, something like that happened in the last few decades. Okay, so this is our mission, right? And this is we founded the Flexcompute, and this is the collection of people who really shared my vision and the founding team of what we are doing today. So how are we going to make this mission a reality? So let me go back to Louis Fry Richardson. Let me just describe the dream of Louis Fry Richardson. So this is an image of, I asked today's AI to generate based on what Louis Fry Richardson actually described in his original 1922 book. So let me read this paragraph. Okay, the paragraph goes like the following. After so much hard reasoning, may one play with the fantasy? So he used the word fantasy, right? That's his dream. Imagine a large hall like a theater, except that the circles and galleries go right around through the space usually occupied by the stage. The walls of this chamber are painted to form a map of the globe. The ceiling represents the North Pole region, England in the gallery, the tropics in the upper circles, Australia on the dress circle, and Antarctic in the pit. That's what the big hall looks like. Now, a myriad computers, well, that's 1922, right? What he means by computers are the people whose profession is to do computing by hand. All right, a myriad computers are at work upon the weather of the part of the map where each sits. But each computer attends only to one equation or one part of an equation. So in today's term, this is one grid point. So each person works on one grid point in the equation. The work of each region is coordinated by an official of higher rank. All right, now in today's term of parallel computing, this is probably one actually rank, right? If you're doing MPI. Numerous little night signs display the instantaneous values so that neighboring computers can read them. That's communication, right, between one grid point and the next grid point. And each number is thus displayed in 3 adjacent zones so as to maintain communication to the north and south on the map. So this is how Louis Fry Richardson is envisioning how weather forecast is being done. Okay, and we also have a grand vision of how do we make hardware innovation as easy and as pain-free as software innovation, right? So this is basically our first step of doing this is basically by offering a suite of simulation tools that's, first of all, many orders of magnitude faster than what people are using today, and also orders of magnitude cheaper than what people are using today. And first of all, Flow 360 is one of these components that offers fluid aerodynamic simulations, aeroacoustic simulations. We also have 3D that offers photonic simulations, and both Flow 360 and 3D are now coupled with thermal simulations. And this suite is just going to expand further and further in the future. And we achieve this by a full stack co-design of basically going from designing and selecting what kind of hardware we're going to put together. And our numerics actually is specifically designed on the hardware, right? So instead of using traditional LAPACK, BLAS, whatever, like we write from scratch the fundamental numeric subroutines on the hardware we select. And on top of that, the math, the geometry, the meshing, the physics. Our primary kind of a core competency is really scalable parallel algorithms for modern hardwares. The goal is to replace repetitive work by our customers through very large-scale computing, so that no human time is spent in geometry cleanup, in meshing, in doing the calculations at all. And with the core competency of scalable parallel algorithms, we are flexible to add features very fast. And the result is we have ultra-fast simulations, provides real-time insight, calculations that are scalable and efficient, and essentially it breaks the limit of traditional computing. Okay, so let's get into a little bit more details of what we are doing today. And before that, going back to Louis Fried-Richardson. So what he did back in his days to actually convince people that this is feasible, his dream is feasible. And think about this in context. That's back in 1922, right? In England, a region where the weather is synonymous to unpredictability. Okay, so what he did to convince people that the weather is not unpredictable is he did a calculation himself. So he spent 6 weeks do calculations with a few of his assistants to reproduce a 6-hour forecast of a relatively small region in Europe. And of course, doing the calculation in 6 weeks to produce a 6-hour forecast is useless, in the sense that a weather forecast is only useful if it actually achieves real time, actually faster than real time, right? You have to do the calculations of a 6-hour weather evolution in 3 hours to predict what the weather is going to be actually 3 hours since you finish the calculation. So this is almost a useless calculation, but it is not useless ultimately, right? It basically inspired the people to work on this weather forecasting, right? Makes it something that ultimately becomes reality. Okay, so now what are we doing today to basically show people that the path towards a future in which hardware innovation is as easy as software innovation is actually possible? So this is our offering of Flow 360, right? High-fidelity CFD with GPUs. Today, we are already reducing the time to solution of from the traditionally what people are using from 10 hours to something like 3 minutes. And the cost has been reduced also by a factor of 2 at least. And this reduction is just going to go further and further as we innovate more on what Flow 360 can do. And we're already offering in Flow 360 a suite of industrially capable capabilities. It's a fully compressible Navier-Stokes solver. And we are offering both the capability of resolving the boundary layers with a white plus equal to Wang mesh, or a warm model that allows calculations to proceed with much coarser grids in the boundary layer. The solver options includes RANS, unsteady RANS, hybrid RANS LES, in which the DDES is the primary workhorse for us right now. And the warm modeled LES is actually online already, so we can also do warm modeled LES. We have very good aeroacoustics calculations, and because we stick with a we stick with a highly accurate scheme, I think we are probably the only industrial level CFD solver that is able to address robustness problems without adding any numerical dissipation. And as a result of that, our aeroacoustic simulation, for reasons I personally don't understand, seems to be able to produce results that's much better than other industrial solver are able to produce. And we have steady and transient viscous flows, and we also have transition models implemented, porous media models for complex physics involving heat exchangers, a low dissipation scheme, as I already mentioned in aeroacoustics. We have an array of turbulence models usually used in industry. And furthermore, we can do dynamic maneuvers and the stability 6 degree of freedom calculations, propeller models, and various kinds of things. And all of them are coupled with user-defined dynamics. So you can put your code into our code to control, for example, how the airplane rotates, how the spinning speed of a propeller depends on the torque it receives, and things like that. And it is robust and accurate. And I think we are at a pretty unique situation that because we are offering the services in the cloud, and we have many customers already who are putting very complicated calculations in the cloud. And that allows us to address robustness problems for the last 8 years without adding numerical dissipation. So basically, we see in real time if any of our customers has any trouble in their calculations, and we can actually dive right into the grid point in which this trouble happens and figure out exactly how to solve this kind of all kinds of robustness problems without sacrificing accuracy at all. And this is something we didn't envision to be a great advantage in the beginning, but it turns out to be one of the key things that a cloud provider can do that traditional software cannot. And so what we have been working on that's going to be released very soon is automated geometry and meshing. So basically, we are going to be offering a service that's based on large-scale computing that is going to automatically fix any geometric problems with no mandatory user intervention. So any unclosed shapes, any nuts and bolts that's not removed can be automatically handled by our geometry engine and meshed in an extremely fast way. And our mesher is scalable to basically arbitrarily large mesh sizes. So in the future, if you are willing to spend the resources to do it, you can do mesh convergence studies to arbitrarily big meshes, as big as you want. And all of this is provided with a web-based visualization. And this is actually our previous generation web visualization. And if you log into flow360.simulation.cloud today, you're going to see something that's even better today. And any calculation you do, you can see right in the web browser. so we also have a Python-driven API. It's actually the same API as the web browser, except for it's basically the API can be called in Python, right? And the Python API allows people to automate the entire simulation process from meshing to configure the simulation, runs the simulation, download data, post-processing. So this basically allows the simulations to be coupled with any workflow you have already. And this kind of a very fast speed and the enormous throughput basically enables people to do very large number of simulations, optimization, etc. Right. So this is one of the simulations we're able to show because we did it internally using open source geometry. We run 350 simulations in a day sequentially, right, to optimize this turbine blade, right? So this is an example of the enormous throughput and what it enables, okay? And now, what is the future? So going back to Louis Richardson, almost 30 years after his visionary book, Numerical Weather Prediction by Numerical Process, the first electrical computer was finally online. And that really made weather prediction able to proceed faster than real time, right? We had the really real-time engineering starting from 1950s. And for us in Flow 360, we are going to evolve everything forward through Flexcompute. But this is a very big dream, and the very big dreams has to be carried by many, many people. And the goal of the webinar today is to invite you, and we already have NVIDIA as our great partner. And we also want to invite you, our collaborators, our partners, our customers, to join us in this dream of making hardware innovation as easy, as convenient, as risk-free, and as innovative as software engineering in the past few decades. And with that, I'm going to conclude my part of the talk and ask if you have any questions.
Before we jump over to the Q&A session of this webinar, just a kind reminder to visit flexcompute.com if you want to have a look at the documentation, some aircraft CFD 101 and CFD essentials. And you'll also see some posts from us in the coming weeks that we'll also join CDFAM and talk a little bit more about hardware innovation and software innovation in a little bit more detail and what that means for the CFD industry. So with that out of the way, I would say let's hop over to the Q&A session of this webinar. And I'm going to be taking your questions right now.
Yeah, I already see a question in chat. Should I address that first?
Yeah, go for it, Qiqi.
Okay, so the question, I'm not sure if everybody can see, is that which numerical method is under the hood of Flexcompute solver? And the question, the answer is that, so from what the customers can see, we are trying to use industry standard numerical schemes. We do second order finite volume schemes, and basically yeah, so that's we do standard for unsteady solvers, right? We do a dual time stepping, and actually steady state solver is just a special case of an unsteady solver with an infinitely large time step size. So from the customer perspective, what we are doing today is almost the equivalent to what other flow solvers are doing. And by the way, like we are a node-centered finite volume scheme, and with a very similar behavior as Fun3D, except for we are as accurate as Fun3D, but much, much more robust. Okay, and all of our innovations happens in the lower level, which is something closer to the hardware.
I think that covers it. We have one question from Sentil, which is about tire simulation. I'll get back to you privately and send you the email address of Qiqi or someone from the team, from the Flexcompute team, to answer that in a little bit more detail. Let's move on to a question for Ian. Accelerating CAE, what are the most significant barriers preventing companies from fully adopting GPU-accelerated platforms for CAE workflows, and how does NVIDIA address these challenges? It's a bit of a longer one.
Yeah, I mean, I think honestly, one of the biggest challenges really is surprising. It's not really a technical challenge. I think sometimes one of the biggest challenges to adopting GPUs is actually just organizational, right? Because a lot of companies are used to their traditional on-prem CPU compute. So moving over to GPU, obviously there's investment in moving to a new tool, in a new technology. And I think sometimes that's the biggest barrier. I think sometimes as engineers, we kind of get stuck in our ways a little bit. So obviously, there can be kind of a barrier there. Other barriers I would say are just obviously for GPU, obviously there's power and constraints around the infrastructure and getting the infrastructure. But obviously one of the ways around that obviously is a lot of the infrastructure is obviously available on the cloud and through SaaS solutions and things like that, like Flow 360. So that kind of takes that piece of it out of your hands. So yeah, hopefully that answers the question.
Mm-hmm. Thanks, Ian. One for Qiqi on Flow 360 for the 100x speed up. Could you explain how this level of performance transforms traditional product development cycles?
Yeah, so basically the speed is really the key, right? So in hardware engineering, basically the two most important factor is one is the accuracy, is how your simulation result corresponds to reality. The closer the simulation corresponds to reality, the better. The second is how effective, what is the efficacy? Basically, can you do the simulation? Can you do enough number of simulations in time for me to actually gain enough insight and therefore to modify my design, right? So these two factors are probably the most important factors. And the second factor is not only speed, but also cost, because if you can do enough simulations in time, relates both to, okay, can I do it with my budget, and also can I do it with my time budget? So being able to do calculations fast and cheap really enables you to do a lot of design cycles. And if you can do it accurately, then you can actually trust the simulation result more and make more detailed modifications with your design in a very fast iteration loop.
Mm-hmm. Excellent, Qiqi, thanks. Let's move over to a question for Ian. How does NVIDIA's AI-driven approach, including frameworks like Modulus, enhance early-stage design feedback in CAE processes?
Yeah, I mean, I think that's the dream, right? Is long term is to move to. Well, I shouldn't say that. I mean, I think first of all, when it comes to AI, I think we have to sort of step back from this or question of AI or traditional methods. I think the real power of AI method is the combination of AI with traditional CAE methods. So, for example, maybe you use Flow 360 to train an AI model, right, to do some very quick, get quick feedback early on in design, but then you'd still obviously use your CFD, final CFD solver to validate, or maybe use your AI model to give you a really good initial solution before you run your CFD solution to speed things up even more. So I think there's so many things that AI can help with when it comes to CA. There's obviously geometry preparation and those things, and that can also be something that AI can help with. I think there's a ton of things to do. I think it's just at the moment, obviously, there's just a lot of it's a new area for people, so people have to get comfortable with it, comfortable with the results, comfortable with the limitations. So I think we're all kind of in a learning process at the moment when it comes to integrating AI processes with traditional CAE.
Absolutely. Next one for Qiqi. Thank you for the inspiring talk. Is Flexcompute working on integrating uncertainty quantification capabilities as part of their pipeline?
Yes, definitely. So this is actually not only uncertainty, but also multi-fidelity, right? So I think like in order for people who are doing hardware to really get as much insight as possible with the fixed amount of time budget and a monetary budget, it is very important to be able to do multi-fidelity simulation, which meaning that you do a vast number of simulations, maybe with higher uncertainty, a smaller number of simulations with lower uncertainty, and maybe even smaller number of simulations with the best accuracy. So we are working on multi-fidelity simulations, and from these multi-fidelity simulations, you can get a sense of what is the uncertainty for various simulations in your simulation toolbox.
Thanks, Qiqi. We have one for Ian on the topic of sustainability. With the increasing emphasis on sustainability, how do NVIDIA's GPU solutions contribute to reducing energy consumption and carbon footprints in engineering simulation?
Yeah, so it's an interesting question, and I think the first thing we have to clarify is ultimately a GPU uses more energy, right, than a CPU, right? But the key when it comes to sustainability is we can get done a lot more work for that amount of energy, right? To do the same performance as a GPU can turn around, then the amount of CPU power that you'd have to use would be, massive. So it just becomes intractable on CPU, and that's exactly what we found with training these large language models, right? It just becomes an untractable problem on CPU. So overall, to get the performance we need to kind of solve these engineering challenges, then the GPU is a more sustainable way to do it. But obviously, it's not reducing the overall energy, right? We're still using energy, but we're using it less than the alternatives to get that level of performance.
Thank you, Ian. Another one for Qiqi. How does Flow 360 leverage automation, particularly in geometry and meshing, to simplify complex workflows? I think that's an interesting one.
Yeah, I think the answer is simple. When we release it, try it. Yeah.
Right. Cool. We'll be following up with the person who asked the question. What role does cloud-based computing play in making high-fidelity simulations like those with Flow 360 accessible to smaller companies or teams with limited HPC resources? That one is for Qiqi as well.
Okay. Yeah, so I think cloud computing actually helps. It's actually something I didn't talk about, but like really something that makes innovation with a small team or much more accessible, like especially for hardware, right? So traditionally, if you want to do very accurate simulations, especially in computational heavy areas like CFD, you have to assemble a HPC cluster. You have people who are like IT personnel to maintain the cluster, and you have to understand the parallel computing. So there is a lot of knowledge, expertise, and resources you have to assemble to be able to do this kind of a large-scale CFD calculation. So with cloud computing, with Flow 360, you just need a laptop. So this actually is one of the aspects that takes a small team much easier, right, to do hardware innovation than what traditional CFD software providers allows you to.
Maybe a follow-up question to that from Thanasis in the questions. One for Qiqi. Why do you think now is the time for this next generation of CFD solvers?
Sorry, what's the question again?
Why do you think now is the right time for this next generation of CFD solvers?
Why do I think it's the time? I don't really think about this question because essentially when we started, right, we looked at whether we should do cloud-based offering based on existing CFD software or we should write our own. And when we do the analysis, it's just clear if we write our own starting from scratch on the most advanced hardware, it's just much better than using existing software. So yeah, I guess it's the right time just because writing something new is that much better nowadays.
That makes sense. Ian, one for you. Many companies face power and cooling limitations in their HPC environments. How can NVIDIA's solutions, such as the H200 Tensor Core GPUs, help overcome the limitations?
Yeah, I mean, it's a problem I hear all the time when I talk to customers, particularly HPC teams. They're like, I spoke to one actually a couple of weeks back at Supercomputing that said exactly that. They were like, yeah, our data center is out of power. Like, we're kind of done. So it is a challenge. And I think there's a couple of ways NVIDIA can help with that. Obviously, like I just spoke about in the last question, and obviously to get the same performance, as you would from CPU, then obviously we can do that with a lot less power with GPU. So that's one way. And another way is actually, obviously, I talked about Grace briefly. Obviously, on your traditional CPU workloads, that can often give the same performance as traditional x86 options, but with half the power usage. So that's another way to to kind of look at using less power as well.
Excellent. And I think we take 2 or 3 more questions, then we'll wrap it up. Do you see any future opportunities, Qiqi, to extend Flow 360 to higher than the second order schemes, as you mentioned, as it's known that HO schemes provide more accuracy per degrees of freedom? You're muted.
Oh, sorry. Yeah, we are already doing that. And so basically, we're going to be opportunistically extend the order of accuracy to higher order when the mesh topology allows. I guess that's the answer.
All right. And then, okay, I think we pretty much covered almost everything. How scalable is Flow 360 for handling small?
Can I just answer one more question? I think there is a question on, are we implicit or explicit? So we are implicit. Yeah, it's an implicit solver. That's the only thing that allows you to run CFD calculations with a well-resolved mesh that's extremely thin. I mean, for aerospace applications, the mesh to resolve the whole boundary layer at the surface is on the scale of micrometers, right? And explicit schemes just has no chance of being able to do things fast enough with a kind of a thin mesh near the boundary layer like that.